Okay, welcome to today's session. In today's session, we'll focus on formulation of power flow problem. So the primary aspect of power flow problem is to find the electrical parameter like voltage, current, voltage angle, as well as power flow and the power injection at a bus for a network. So in order to do that, let us start our approach with a simple power system having 4 bus. So we have 2 generators here and 4 bus. In addition to that, we have a transmission line, generator, transformer, something like that. But let us focus on a circuit which has a simplified network of 2 generators, this transmission line and 4 buses. So in order to proceed to the formulation of this power flow problem, first we have to remember a Norton equivalent circuit for this generator. So in this representation, we have generator and internal impedance for both generator. So to proceed to the power flow analysis, first we have to convert this Thevenin equivalent representation of generator to Norton. So to do that, we divide internal voltage with internal reactance of the generator. Then we put them as a parallel and connected to the bus. For example, for generator 1, we have 1 ohm impedance. So when we take the inverse of this, become minus 1J, which is the impedance between bus 1 to the ground. Whereas we have current source I1, which has a magnitude of E1 divided by this reactance. Again, for a generator also, we'll repeat the same thing. So for generator also, we have E2, then impedance of 0.8. So in order to perform the power flow analysis in terms of Y bus, we'll convert all impedance and the reactance of the transmission line to admittance. So for example, here we have one ohm reactance. When we take inverse of this and represent as admittance, we have minus J1 ohm. Again, for this transmission line, also we have impedance of 0.4. So when we take the inverse of this, become minus 2.5 J, this magnitude, and we'll convert all the impedance into the admittance, and they will form the voltage current characteristic equations for that. So, for example, for the transmission line from bus 2 to bus 3, here from bus 2 to bus 3, we have 0.2 reactance. So the admittance equivalent of this obtained as 1 over 0.24. So it becomes minus 5 J O. So to proceed to the power flow analysis and obtain the power and the current characteristic equation as a parameter of other electrical components like voltage and the voltage angle, we will perform a KCL for each bus. For example, here we have for bus 1, we have I1, which is a magnitude of a current injected from a transformer to bus 1. Again, we can consider all remaining current will be drawn from this bus. For example, to the ground, this is I note from bus 1 to bus 2, I12, which is following from bus 1 to bus 2. Again, from bus 1 to bus 3, which is I13, we can consider it as the current is going from the bus 1 to another circuit. So to perform that, we can write a KCL equation for each bus. For example, if we consider bus 1, the input current is I1. So this I1 is equal to the current drawn from the bus 1 through this ground resistance, and the magnitude of the current flowing from bus 1 to bus 2 and the bus 1 to bus 3. So we can represent magnitude of the current going from bus 1 to the ground as V1 divided by this reactance. Again, the current flowing from this bus 1 to bus 2 as the voltage difference divided by this impedance. Again, the current running from bus 1 to bus 3 as a voltage difference between V1 and the V2 divided by this impedance, because current is defined as the ratio of voltage difference divided by the impedance. So when we take the admittance, we can specify current as a multiplication of voltage with admittance, because if it's impedance, current is obtained as voltage over impedance, but we convert all parameters to the admittance, we can represent a current as the multiplication of voltage with admittance. So applying a KCL to at bus 1, we can obtain this equation. For example, I1 is input current, which is equal to Y1 naught, means is the admittance from bus 1 to ground multiplied voltage 1. Then the admittance from bus 1 to bus 2 is represented as Y12, and the current flowing from bus 1 to bus 2 is V1 minus V2 multiplied by admittance. So this is the current flowing from bus 1 to bus 2. Again, to obtain a current flowing from bus 1 to bus 3, we'll consider V1 minus V3 multiplied by this admittance. So the I13, which is obtained as Y13 multiplied by V1 minus V2. So for a bus 1, the KCL is obtained as this equation. Again, for a bus 2, we can consider the current of generator 2 is injected to this bus, whereas the current is going to the ground from bus 1. Again, the current is going from bus 2 to bus 1. Again, the other current magnitude is going from bus 2 to bus 3. So we can apply the same principle like we have taught for bus 1 to bus 2. So I2 is equal to Y20. Y20 means is the admittance from bus 2 to ground multiplied by V2. Y12 means it's like the admittance of a transmission line between bus 1 and the bus 2. Then V2 minus V1 is the voltage difference between bus 1 and the bus 2. Again, plus Y23 means it is the admittance of a transmission line between bus 2 and the bus 3 multiplied by V2 minus. Again, for the remaining bus 3, for a bus 3 we don't have any injected current, we can keep it 0. So this magnitude is equal to the current going to the bus and leaving from the bus. So if we assume all current is going from bus 3 to bus 1, then bus 1 to bus 3 to bus 2, then we can write the same principle for V3. So 0 is equal to is the injected current from a generator is equal to 0. Y23 means it's the transmission line admittance between bus 1 to bus 3. V3 minus V2 is the voltage difference. Here we have V3, here V2. Then difference is divided by this, and we obtain a current between this. Again, for V1 between V1 and V3 also, we have V3. Then taking the difference between V3 and the V1 and dividing by this impedance will give a current. So we obtain this between bus 3 and the bus 4 also the same thing is going. So when we come to bus 4 again, we don't have any generators. Let us assume the input current is 0, but this 0 is equal to the magnitude of a current flowing from this to this, and we can obtain that by taking Y admittance multiplied by a voltage difference V4 minus V3, and this is equal circuit. So if we simplify those equations, we can obtain this I1, Y1 naught, Y12, Y13 multiplied by V1 minus Y12, V2, minus y13 v3. For I2 also the same, minus y12 v1 plus y20 y12 y13 v2 minus 5. So if we rearrange the same parameter like v1 v2 and take the common multiplication, we can come to this simplification. For example, what we call a diagonal matrix is obtained as a sum of all admittance connected to that. But for example, y11 is the summation of all admittance connected to bus 1. y22 is the summation of all admittance connected to bus 2. y3 is the summation of all admittance connected to bus 3, and the y44 is the summation of all admittance connected to bus 4. Whereas y12 is the admittance between bus 1 and bus 2, which is equal to the admittance between bus 2 to bus 1, because the same transmission line is observed from different sides, and those magnitude equal to minus the admittance of a transmission line. Once we obtain the impedance of transmission line, we obtain the admittance of transmission line by taking the inverse of that magnitude. Then for the non-diagonal matrix, we can obtain as y13 is equal to y31 as negation of y13, or y31 is also similar to this. So we can represent our final equation by using this equation, so that I1 is equal to y1, y12, y13, y14 times 4. I2 is equal to y21, y22, y23, because we have a definition for y21, y23, y2, so like that. So we can represent this as a matrix formation. So we have I1, I2 up to In for any bus number. So we have also a square matrix. We have y1 up to yn, then yn1, then v1, v2, v3. So we can represent this as a equation, a matrix equation, so that I bus is obtained as y bus times v bus. So to obtain a v bus, we can take, we can multiply both sides of equation by y bus inverse, so that we can calculate the magnitude of a bus voltage. This is very simple. So the y bus formation is very straightforward. For example, what we say, y11 is the summation of all admittance connected through bus 1. For example, here is y bus 1. y1 is obtained as minus 1 plus minus 2.3 plus minus 5, which is 8.5, minus 8.5. So y12 is the bus admittance connected between bus 1 to bus 2, minus 2.5. That's the negation of minus 2.5, because the negation is here. So like that, we can calculate all the y bus matrix. So the diagonal matrix, for example, y11, y22, y33, and the y44 is the summation of all admittance connected to each bus. For example, for y44, all admittance connected to this is minus 12.5. It's minus 12.5. For a bus 3, minus 5 is there, minus 5 is there, here 12.5. So it becomes 22.5. 22.5. Again, for y33, for y22, or this magnitude is the summation of this. But for a diagonal, for example, this is y1, this is y12 is equal to y21. y13 is equal to y31, like that. So the diagonal matrix is the summation of all admittance connected to that bus, whereas then off-diagonal matrix is taken as the negation of the admittance connected the transmission line between those two bars. For example, If you want to take the y13 means here 1 is 3, we have admittance of minus 5, so we'll take the negation of these as 5. So y13 is 5 or y31 is 5. You can see that y31 or y13 is 5. So we can calculate the admittance matrix by using this scheme. So coming to a power flow problem using this admittance matrix, we can use the same principle that we have tried to see in that diagram to perform a power flow for n bus. For example, here we have n general bus system, so that we can perform n by n y bus matrix, and we can calculate the voltage, power, current, and all things. So, for example, we have bus 1, bus 2, and the bus n. There is a admittance between bus 1 to bus 2, bus 2 to bus n, bus 1 to bus n, something like that. So, we'll perform a bus admittance matrix by using the previously defined equation. So, for off-diagonal element, mutual admittance between I and j is equal. So Yij is equal to minus Yij. Yij or Yji is similar series admittance between bus 1 and the bus is taken as the negation of a bus admittance. But for diagonal elements, which we to call a self-admittance at bus I, we will add all admittance connected to that bus. So that Yi is equal to the summation of k from 1 up to n for a k different from Yik plus Yi shunt. So we will perform n by n matrix for n bus distribution network, and we can perform the final solution by using this. I is equal to Y bus times V. So if we want to get the voltage from a current, we will multiply both sides with the inverse of Y bus. So the bus voltage in the current equation can be related to each other by using a polar form of equation. For example, when we say VI can be represented as VI magnitude at angle of sigma I. This means this sigma I can be written as a complex as sine and cosine. So we can obtain the voltage and bus relation by using a KCL by considering the injected current as bias is the same as the current that will follow from the bus. So a simple current equation for a bus I is obtained by using this equation. I is equal to the summation of Yij, Vj, j starting from 1 to n, or I bus is equal to Y bus times. So we will apply this simple equation to determine the relation between current and the voltage. So when we say I bus means for n bus we'll have different bus. So the magnitude of current H bus is taken as a transpose of this magnitude I1 up to In transpose represented as I bus, whereas V bus also V1, V2 up to Vn transpose. And in addition, the Y admittance or Yij can have reactance as well as resistance component. So we can have this format. We can have this format, which is conductance Ij plus admittance Ij. So the conductance is a real part of admittance, and this is the reactive part of admittance. In addition, for a voltage also, when we say Vj, Vj is a magnitude at angle of theta j, so we can have this expression, which is this has also both real and reactive part. So in order to represent the total final equation for a current is obtained as Yij times Vj, but Yij can have these two components, the conductance plus admittance. then the VJ can have this representation, the voltage angle of path J. So if we want to write it in general terms, Ij is equal to conductance Ij plus the imaginary part of the admittance times Vj. So we will use this equation to represent the final I and voltage relation. So if we want to represent that Ij as a complex number, we can write conductance can have multiplied with both imaginary and real part of the voltage, because this voltage can have this magnitude. We can represent the voltage as cos theta j plus j sine sigma j. This is a complex form representation of Vj. So when we see this Vj here can be represented like that. For example, this can be represented as Vj into cos sigma, cos of sigma j plus j sine of sigma. So here what we did is that I is equal to Vj multiplied by conductance times the angle part of the voltage plus the reactance, the imaginary part of admittance multiplied by this magnitude. So this gives a current at path as a function of all paths. So it's very simple. So the easiest way to find a current at each path is obtained by using simple equation. So I is obtained as conductance plus admittance is the imaginary part. We can express this voltage also as complex number, so that the complex number notation can be used to find the current at each path. In addition to that, a power injection or power flow equation is also possible to calculate by using this power flow equation. So the magnitude of power is represented by Pi plus J cubed, when this J indicates the reactive power of the component. So the general apparent power is obtained as V times I conjugate. So we have V, then we have I, the I representation of this, then we make a conjugate of the component. So when we say a conjugate, it means for a parameter which is represented as magnitude at some angle, when we make a conjugate, we take the negation of the angle. So for a real part, we can take the cos of the conjugate. Again, for a reactive part, we'll take the sine of the conjugate. So here we have Vi is as this. We have Vj is also as this. We have Yij, which has a component of this conductance Iij plus Bij is there. So we have this Bij. Again, the Bij have an imaginary part. So, but we have this Vi have an angle sigma I, and this has a angle sigma j. So when we take a negation of that, these angles will be taken as a negative, and the multiplication for that total angle is taken as the difference between sigma j and sigma I and the sigma j. This is the angle difference due to the conjugate of this. When we make a conjugate, Vj will take a negative angle of the representation as a negative sigma j. For this we have sigma I. Then when we multiply a number, complex number represented as magnitude as some angle, for a multiplication we will add the angle. So it becomes sigma I minus sigma j. So for the conductance part, we have a real part, then the cos part will be a real part. But for this, the imaginary part of impedance, we have imaginary part of the voltage, so that's why it becomes sine theta I minus theta j. But when we come to the reactive power, this part become a sine and this part become a cos, because cos is a real part. We have imaginary part as conductance Bij. So this is the final representation of the power at bus I and the bus Pi and the Qi. So once we get a current using Y bus and the Vi and calculate the Pi and the Qi, so since the imaginary part of conductance as J, here it becomes the real part of the voltage component. So we can calculate the voltage, the power by using this equation. So it's very easy now. It's very straightforward. Once we obtain the current from a voltage and the Y bus, and once we are obtaining that, we can easily calculate the magnitude of Pi and the Qi at each bus. And we can calculate also a power flow by taking the difference between a bus. For example, if we want to calculate the power flow between bus I and the bus J, we can calculate the power at each bus and take the difference, so that the power flow will be the difference between each bus. So Pi and the PR is specified or calculated at each bus. This equation are nonlinear V and so this is a simple way to calculate the power flow equation. So let us recap what we have learned up to this time. So in order to calculate what we have said, we have to first identify the type of a bus. For example, if we have a slack bus, which is a mandatory, at least one bus will be a slack bus when we are carrying a power flow analysis, the voltage and voltage angle is specified. Again, if we have PQ bus, the P and the Q will be specified. Again, for a PV generator, we have specified P and voltage magnitude. But the magnitude of voltage angle in the Q will be unknown and it can be calculated. But when we are using a PV bus, we have to keep in mind that the Q should be limited between the maximum and the minimum of the rating. For that matter, when we are considering the swinging bus, so we have to consider that the P and the Q should not exceed the limit. Again, we have a load bus. For a load bus, both P and Q are specified. Voltage will be unknown. Physical meaning of those parameters. For example, when we say P and I, it is a net real and reactive power injected into a system at bus I. Vi and alpha is voltage and voltage angle at bus. So by using this, we can calculate the voltage magnitude, voltage angle, power at each bus, and power flow. So the purpose of performing a power flow analysis is to determine the parameter we try to specify in this lecture. So we have different algorithms, among them gauss sidel is the simplest algorithm to perform a power flow analysis. So especially when we are calculating a voltage and a current relation using a simple linear equation, gauss sidel is the most efficient method to calculate the voltage and the current using iterative method. So the gauss sidel is used for a linear equation where the equation have this form is AX is equal to B. When we say AX is a matrix, when X is a variable to be determined, and the parameter B is a constant. So for a system equation having these, for example, for the first equation we have A1, X1, A1 to X2, A1 and Xn up to this is equal to P1. And again, we have the second linear equation of multivariable function as A12 up to A2n Xn is equal to B2. And this continues for the n number of equations where we have an1 x1 up to an xn is equal to bn. So to solve this equation for this main diagonal variable, what we call main diagonal variable means we have n by n matrix. So we will solve for a diagonal variable which is x1, x2, x3 and xn. So to perform that, we will take other parameter except this diagonal to the left side. For example, for a11 x1 plus a1 to xn of 2, a1 and xn is equal to b1. If we take all variables or remaining component to the left side, it becomes b1 minus a1 to x2. So for diagonal variable, if we do the same things, we'll get the a xi is equal to 1 over, for example, if we take this all variable to this side, b1 minus a1 2, a1 3, a1 4, like that, divided by this variable a1 1. So we can write in terms of ij to get the general representation to solve the variable, diagonal variable using gauss sidel. So xi k is equal to 1 over aii. Ii means it's the coefficient of a diagonal matrix. For example, for x1 it's a11, for x2 it's a22, for x3 a33, for xn it's ann. So we can use a general equation as xi next iteration is obtained as 1 over ai into bi minus the summation of j from 1 to I minus 1 aij xj k plus 1 minus the summation of j starting from I plus 1 up to n aij xj k. So from this equation we have around 6 components. Xi k plus 1 means xi next iteration is obtained as the ratio of ai means it's a constant coefficient of a variable, diagonal variable. Bi is a constant minus the summation of aij xj k plus 1 iteration starting from j plus j1 to I minus 1. So when we are calculating xi, we are using a new updated value of x for ai minus 1. So for example, if we are calculating x2, we'll use x1, update a new variable, but x3 will be the oldest will be used. That's why in this equation we have the summation of ai xj raised to k starting for a j I plus 1 up to n. So we'll use updated value for xi when xi have many variable and we have some updated and some previous version. For example, if we assume that there is 3 variables, so we are calculating x2. For x2, we'll use updated value of x1, but we use old value for x3. Again, when we are calculating x3, we have already new calculated x1 and x2. So for that, we use updated version of a variable. That makes this scheme to approach the desired solution quickly. So the general algorithm for this gauss sidel is stated in this topic 4. It says algorithms for this step. First, we will arrange the equation to isolate a diagonal variable. Like I've said previously, we have a11 x1 up to a1 and xn is here. So we will arrange a diagonal variable to obtain the diagonal variable as a function of other representation. So we choose the initial value. So when we are using gauss sidel, we will arrange our equation to make our equation easy to replace another variable for a calculation. So this equation is used for that purpose. So what we'll do is we'll arrange that so that we can easily replace the variable. Then we'll choose initial guess. For all variables, take initial guess. For I up to 1 to n, compute next using the latest value available for those data. So, for example, if we start with a 0 iteration with initial guess, then start calculating a new iteration. First iteration, we start from x1, then x2, xn. So for x1, we'll use old or estimated value. For x2, already we have calculated value of x1, then we use calculated value for x1 and old or estimated value for the remaining x. So like that, we use updated value for. That's why in this equation we say aij xj k plus 1, new version of calculated variable we used for variable xi less than xj when xj is a variable to be calculated. Then compute the error. We'll calculate the error, the maximum error between the iteration, for example, iteration 1, iteration 2, iteration 2, and iteration 3. So maybe the stopping criteria is based on the change of error. If the error is less than the minimum value, probable value, we can stop the iteration. So what makes this gauss sidel very important is the converge if the matrix is diagonally dominant or systematic positive definite. So the gauss sidel will converge quickly if the coefficient AA1, AA22, AA33, AN is positive and have high magnitude compared to the remaining coefficient of a variable. Use the newest update values in the same iteration. Yeah, it's already said. For example, if we are calculating x3 or x4, so we have already updated value for x1, x2, x3. So we'll use the updated value, but we use the older version for x value greater than the value to be calculated. So the general flow diagram is that we start the algorithms by rearranging the equation, input variable in tolerance, then we'll do the first calculation, then we check the error, then if the error is greater than tolerable value, then we complete the next iteration. So the stopping criteria based on the error changing. Let us see these algorithms by using an example. For example, here we have a 3 equation which is a linear equation. So like previously we tried to state, we have x, y, z is equal to 12. So this is a diagonal coefficient. This is a diagonal coefficient. So a11 is 10, a22 is 10, a33 is 10. But we can see that if the diagonal is positive and the dominant, the gauss sidel can converge easily. So rearranging and solving for the diagonal variable. So we put the diagonal variable as a function of another. So for example, for this, for x we can obtain 12 minus y minus z over 10. Again for y also the same, for z also the same. So we can put the initial guess. If we take a value of 0 for all and the tolerance E is equal to 10 raised to minus 4, we can compute the first iteration for this equation. So the first iteration can be obtained by this equation. For example, if we guess the initial 0, 0, then the next first iteration for variable x is obtained 12 minus 0 minus 0 over 10. It becomes 1.2. 1.2. So again, we can use the same principle because look here, we have a new updated version and old version. When we come to y, again for a y, we have this equivalent representation or expression. So we have a new calculated value for the value x from the first iteration. So we will use a new value for the value of x, and we don't have any new calculated value for z, so we'll use the old. So to calculate the new value of first iteration for y minus y is equal to 13 minus 2 times the new value of x is 1.2 minus 0 over 10. So it will become 1.06. But when we come to z, for the first iteration, we have 0 value for all three variables, but we have a new calculated value for x and y, but still we are calculating a new or first iteration for z. So to calculate that value, we'll use a new value of x and y for z. So z is equal to 12 minus 2 times 1.2 minus 2 times 1.6. So it becomes 0.94. This is the first iteration. So now what we'll do is that we will calculate the error. The error is the difference between first iteration and the second iteration, or this is the difference between k iteration and the k plus 1 iteration. So if we take the change in error for the first variable x, the first estimate is 0 and the new calculate is 1.2, so the error is 1.2. Then for the second variable y, the initial guess is 0 and what we calculate is 1.06, so the error is 1.06. So this is the error for the first iteration. The first iteration, the error is 1.2, maximum is 1.2, and the for variable y, the error is 0, minus 1.06, and this is so the maximum is this. So we can pursue the second iteration. When we are doing the second iteration, we use the first iteration result to calculate the new y. So for example, x is equal to 12 minus y is what the value of 1.06, that is 0.94 over 10. So we'll get 0.99. Again, for a second iteration, we'll use first iteration for a variable greater than g, when the g is a variable to be calculated, and a new updated value for a variable having a coefficient less than g, when g is a variable to be calculated. So what to do is that, for example, when we are going to do the second iteration, we have a second iteration for x. Again, we are going to calculate the value of y after second iteration. So y is equal to 13 minus 2 times x. For x, we have a new one, 0.99. For z, we have already calculated alt, which is first iteration, 0.948 divided by 10. So we'll get 1.05. Again, for z, we have this equation. Again, we have a new updated value for a second iteration in case of x and y. So we'll use this updated value for z. So it becomes 40 minus 2 times x means 0.992, y means 1.05. So the values obtained is become 0.991. So the maximum error is obtained again by taking the difference between a new iteration and the previous iteration. So the new iteration is 0.99 for x, for y also. So if we take the difference, the maximum difference error is 0.2. Again, we will go for next iteration. So when we are going for a next iteration, for x1, we'll use a new old value of second iteration, y and z to calculate a x1. So replacing the value of y and z with 1.0054 and 0.991, we'll get this value 0.996. Again, for y also, we'll replace the value of x with a new one, 0, and the value of z with alt, 0.9891, and we calculate the same. Again, for z, we use a new calculated value of second iteration, and we get 1.0. So again, the maximum error is calculated by taking the difference between this new iteration and the previous iteration. So we'll proceed in the same way, and finally we'll calculate the value of variable at stage 4, and we'll get the value of x is 1, the value of y is 1, and so at that time the error is less than the pre-specified error, so we can stop. We can check whether the solution is correct or not. So in first equation we have 10x plus y plus z is equal to, so if we replace all variables 1, it becomes 12, so it's perfect. Again, if we replace all variables with 1 in the second equation, 2 plus 10 plus 1 is 30. Again, if we replace that in third equation, it becomes 40. This is how we can solve the linear system equation by using a Gauss seidel. One important update of this Gauss seidel is that this Gauss seidel is very simple because it uses updated value as soon as they are available. For example, when we are calculating a second iteration, if we have any calculated component for second iteration before a variable to be determined, we use the updated value. This will accelerate the approach to the solution. Generally, converge after faster than other methods. So convergence is good, simple and memory efficient, widely used for solving large space linear system. So we can apply this system to the power system also. So by using this method, the solution is obtained after fourth iteration and is perfect. The second method that we will use when we are getting a power flow analysis is a Newton-Raphson method. So Newton-Raphson method is very suitable for nonlinear system having n variable equation. For a Gauss seidel, we see that it's appropriate for a linear system so that the iteration can be performed by deriving an equivalent representation for a diagonal variable and taking the iteration continuously. But when we come to a Newton-Raphson, we'll use this for nonlinear system. So in case of Gauss seidel, we'll have any number of functions, for example, f1, f2 up to fn is equal to 0. So we'll perform the function into a matrix form. We have a variable x which represents this xn, x2 up to xn, whereas fx can also represent this different function. So in matrix form, we'll perform this representation to derive the equation for a Gauss seidel. So the basic concept that we have to understand when we are using a Gauss seidel is a Jacobian matrix consisting of first order partial derivative. If our function has any number of variables, so we have to take the n partial derivative of a function with respect to each variable. For example, what we call f1 is a function, nonlinear function among a multiple function going to be solved. So we'll take a partial derivative of first equation with respect to x1, with respect to x2, up to with respect to xn. And we'll make a Jacobian matrix in the same scenario for all. If we have f2, also will take the partial derivative of function 2 with respect to x1, the partial differentiation of function 2 with respect to x2 up to xn, and we'll make n by n matrix. So in doing that, what we'll do is that in Newton-Raphson, like a Gauss seidel, we start with initial. So once we make a Jacobian matrix, we will estimate the initial guess for all variables. So the initial guess is very important to determine. So we will evaluate the function as the initial gas. Then we will evaluate a Jacobian matrix as the initial gas. So once we make our Jacobian matrix in terms of a variable, then we take the initial gas, then we evaluate the function or function, any function at initial gas, then we will calculate a Jacobian matrix at initial gas, and then we will solve a linear system equation for a variables change. So the equation to be solved is that the Jacobian matrix multiplied by change in x as k iteration should be equal to minus the evaluation of a function at that iteration. So we'll solve this equation and check or calculate a new updated variable by using the equation depicted here, the way to obtain the updated value. So the updated value is obtained as the initial gas plus change in variable. So if we have 3 or 4 variables, then we calculate n by n Jacobian matrix. We will use the initial estimate to calculate the value of the function at initial estimate. Then we'll calculate a Jacobian matrix. Then we'll put our equation to get change in a variable at k iteration. So the Jacobian matrix multiplied by change in x equal to minus the evaluated value of function at iteration will be solved to obtain the value of correction vector. So that the value of correction vector will be added to the initial gas to get the value of a variable at the iteration level. So again, we'll check the maximum error at that iteration, and we'll repeat the same scenario if the error is higher than pre-specified or tolerable value, and we'll repeat for the next. So when we are going to repeat we have already formed the Jacobian matrix in terms of variable. Then in terms of initial gas, we will use a new updated value for variables. Then we evaluate at a new updated value the magnitude of function. Then we'll form a Jacobian matrix calculated using updated value. Then we'll bring the Jacobian matrix a new correction value with a new evaluated value of the function and determine a new correction value. That new correction value is added to the value of a variable obtained at a k iterated value to obtain k plus 1 value. So we'll proceed in this way. So the general flow diagram, a schematics to use a Newton-Raphson is depicted here in the flow diagram. First, we will choose the initial gas at k is equal to 0, what we call initial estimation. Then we will evaluate the value of a function at initial estimation. Then we will evaluate the value of a Jacobian matrix at initial state. Then we will solve this equation. The value of Jacobian matrix times correction value is equal to minus the value of evaluated function at initial gas. So the updated value will be obtained by using xk plus 1 is equal to xk plus correction value obtained for k. So we'll check the convergence value, whether the error is within a required magnitude of range or not. If not, we'll return back to evaluation of function value in the Jacobian matrix at a new obtained value. So E is a tolerance value. Good initial guess improve a convergence system. Like for a gauss sidel also, if we have a good initial guess, the iteration will converge quickly. In the same sense, if we have initial guess, we have a good convergence for a Newton-Raphson. Jacobian matrix must be non-singular. Newton-Raphson has a quadratic convergence near to the solution, while it is real. As soon as we are approaching the solution, the convergence is high. The application of this Newton-Raphson is highly valuable in the power flow study, since it is a non-linear equation in terms of calculating power and what's coactive and reactive power. So the algorithm is very simple, very simple. What will be that? We will take a first initial gas, then evaluate the value of function of initial gas, evaluate the value of Jacobian matrix, then solve the equation, which is the multiplication of Jacobian matrix with a correction factor is equal to minus the value of a function evaluated at initial gas. Then it's easy to get the updated value for a variable where x plus 1 is equal to xk plus change in k. Then we'll calculate the magnitude of error and repeat the same thing until the convergence is reached. So this is a new Newton-Raphson method. So let us see with example how Newton-Raphson is used to solve the nonlinear equation of the variable. For example, we have function f2 and f1, which has representations of this x squared plus y squared minus 4 is equal to 0, x minus y is equal to 0. So, well, as I tried to say previously, first we make a Jacobian matrix. We'll take the partial derivative of first function with respect to variable 1, again with respect to variables. So it becomes 2x and 2y. Again, we'll take the partial derivative of second function with respect to x and y. So it becomes 1 and a minus 1. Then we'll use equation, iteration equation, where a Jacobian matrix multiplied by a correction variable is equal to minus the value of the function evaluated at the initial gas. So the next value of a variable is obtained by adding a correction value to a previously used initial gas, so that we can obtain k plus 1 iteration by using this equation, by summing the previous value of a variable plus a correction factor. So if we take the initial value of both variables, x and y is equal to 1, and for perform the Newton-Raphson iteration scheme for the given function, first we will evaluate the value of a function at a initial gas. It becomes minus 2 and minus 1. Again, we'll calculate the value of a Jacobian matrix. By substituting the value of variable with initial gas, it becomes 2, 1 and minus 1. Then we'll apply a iteration equation where a Jacobian matrix multiplied by a correction value is equal to minus the value of a function evaluated. So we have minus 2 minus 1 to become 1, 2. So by solving for the value of change in x and the change y, we can calculate a new updated value. This can be obtained by multiplying the both sides with the value of Jacobian matrix numbers. So a new updated value will be obtained by using that. So since Jacobian correction value is obtained 1 as 1 for change in x and 0 for a change in y, a new updated value will be for x1, the initial value is 1 and correction factor is 1, become 2. For y1, the initial gas is 1 and the correction value is 0, then we obtain the updated value of x and y. Again, we'll repeat the same scenario. We calculate the value of the function at a new updated value, calculate the value of Jacobian matrix at updated value, then we will perform the same scenario that we have did for the initial gas. For example, by substituting x is equal to and y is equal to 1, the first equation becomes 1, the second equation becomes 0, the value of the function evaluated is this. And again, Jacobian matrix becomes 4, 2, 1, minus 1. Then we go to the equation where the Jacobian matrix multiplied a new correction value is equal to minus the value of the function evaluated at a given sharpness. So again, we'll solve for the value, a correction value for the first iteration. So the change in x1 become minus 1 over 6. Change in y become minus 1 over 6. So we'll add that to the value of the x and the y obtained for a first iteration. So on the second iteration, x become 2 minus, because it's a new updated value, plus change in correction factor become linear. Again, for y also we have updated value of 1, and we have a correction value of this, so this become 0.833. If we proceed for a third iteration, we have a value of x and y obtained from second iteration. Again, we'll go for evaluation of function by using the value obtained in the second iteration. So it becomes 0.027 and 0. Again, Jacobian matrix at second iteration of the 3.36, 1.1 minus 1. Again, we'll solve the change, Jacobian matrix time change in correction value at second iteration is equal to minus the value of function evaluated at second iteration. And by solving that, the value of change in x is obtained as 0.05, and the value of change in y is obtained as 0.0. So after third iteration, again we add the change in variable or correction value to the previously obtained updated value, and finally we get the value of x as 1.823 and the y as 0. So if we check the value for the maximum convergence, we can see that after third iteration, the system is correctly matched with what we have said. But the stopping criteria is based on the change in error. So since change in error is very small after third iteration, we can stop it here. But always what we have to remember, the stopping criteria. The stopping criteria may be based on change in error,